Welcome to this first lecture of EE557. So this course is called Estimation Theory, and its code is EE557. And I am the instructor of this course. My name is Umut Orguner, and I will be teaching this course through the semester. So remember that this course the title is Estimation Theory. So this title is unfortunately an obsolete title for this course. If you remember, if you have taken the course EE501 in this department, then you might remember that the title of that course is Linear Systems Theory. But in the first lecture, I generally talk about the fact that there is no system in that course. So it is only the linear algebra. That is because that name is an obsolete name. So this course was years before proposed by Professor Mübeccel Demirekler. And at that time, the course was structured to cover the estimation theory. But over the years, its content has evolved, and it came to a point where the course is not only estimation theory anymore. There is also some control in this course. So if I give this course a couple of years consecutively, then I will try to change the title of the course so that the title represents the course content in a better way. So and in that case, the title that I would give this course would be the following: Stochastic Systems. And in this case, we will think about both the estimation and control. Okay? So we are going to think about stochastic systems in this course, and we are going to think about both the estimation and control. So this would be a more representative title, and it would be in harmony with the overall content of this course. So what is this course about? It is going to be about the following type of systems. They are called dynamic systems. So if you don't know what dynamic system means, then you should probably take the course EE502 in this department, which is about linear system theory. So it is here xk equals, so let us say xk plus 1 is equal to f of xk, uk, and wk here. And we also call something as measurements yk, and these are h of xk. They can depend on uk, and furthermore they can depend on some other variable which is vk. So here this is called the state equation of the system. These are discrete time systems, and this is called the output equation. And here xk is the state of the system. It is in general a vector, and uk is input. And here, so we have defined what these two are, and wk is called the process noise. Okay, and these are representing the inputs for the system which we cannot control. The user of the system cannot control this wk, and actually we are going to model this wk as a random vector. So that is going to be inputs of the system that cannot be controlled by the outside user. uk, on the other hand, can be controlled by the user of the system, by us, and therefore uk is the controlled inputs or controllable inputs, and wk are the uncontrollable inputs of the system. So, and this vk, they are called measurement noise. Okay, so this is yk, the output of the system, is actually a function of the state, the inputs, and some noise term. So these noise terms are so this h represents the sensor, by which we sense the output of the system from the states and the inputs, and Vk represents the imperfections in that sensor measurements. We know that any measurement device is susceptible to noise, and we cannot, in many cases, measure the state exactly. So we would measure it with some contaminating noise here. Okay, so here, this is the general framework that we are going to have, and sometimes xk will take elements in a finite set. Okay, so sometimes xk is going to take its elements from a finite set. In that case, such a system would be called a finite state system. Okay, so in that case, I have finitely many, I have countably many, and I have finite number of states that the system can have. So an example of such system would be called a Markov chain. And we are going to see what a Markov chain is and what we can do with it, or how we can use it to model some real phenomena in the world. And sometimes, on the other hand, xk is going to take elements in values in Rn. So in that case, it would be uncountably many elements in the state space. So in the first case, state space is composed of finitely many elements, and in this case, in the second case, I would have the uncountably many elements, infinitely many elements in the state space. State space is in that case Rn. Okay, and such systems will be actually continuous state systems, or in that case finite state systems and infinite state systems in that case. So here we are going to be working with this system, and we are going to have an objective. So remember, what is control? Control is selecting the inputs of the system. The inputs that we can select are UK. Selecting UK such that the system behaves in a manner that we would like. Okay? So we would like to select the input here, and then we would need to have some objective. So that is called the optimal control. So we will have some objective, and here the input values will be changing from 0 to k, and this objective, for example, a very easy objective can be I from 0 to n minus 1 xk squared. Suppose that n is 1, and suppose that I have a state which is a real number, and suppose that I would like to minimize such a cost function by choosing the inputs. Of course, states are determined by the inputs here. Okay, so I need to select these inputs such that such an objective is minimized. So in some way, I want xk, the states, to be small, because I'm trying to minimize their squares. Okay? Here in this problem formulation, in this objective function formulation, there is a problem. Okay? So, and that problem is that we never know what xk is. Why is that? Because there are some random terms in this equation. Wk, the process noise, is unknown to us. But there is something known, and that is going to be the statistics of Wk. Okay? We will know, for example, its expected value. Expected value of Wk will be known. Or we will know the square of expected value of the square of the Wk. So we will know some moments of Wk. And in the most general case, we will know the probability distribution of Wk. Okay? So we will never know what Wk is in in real life, but we will know its statistics. So the WK represents some uncertainty in the system, which we generally call a disturbance. It's an input that we cannot control, and we are going to model WK by using its probability distribution, P of WK. Okay? And since we know only WK, and since WK always enters into xk plus 1, xk and xk, so we will see that such a cost function is meaningless. I really cannot calculate this cost function because in general I don't know what xk is. Xk is a random variable and it is dependent on some unknown random variables. Okay? So we will never know what xk is, but therefore we will never be able to calculate or minimize such a cost function. So then what are we going to do? We are going to use again our probability knowledge. So instead of minimizing such a cost function which we can never calculate, we will minimize the expected value of such a cost function. Okay? In that case, since I know the statistics of WK, then I will be able to calculate such an expectation. So this cost will be a calculatable cost function. And then the problem is going to be to minimize, okay? So to minimize this cost function use over U0k, and then I'm going to find those optimal inputs. Okay, these are, I'm going to call them as U hat 0k. Okay, this is called the stochastic optimal control. Optimality comes from the optimization problem, and the stochastic part comes from the stochastic structure of the problem, and control comes from the fact that we are trying to find the input of the system, and by applying as stochastic optimization. Okay. So here, in general, we will try to also, instead of selecting optimal use in this way, sometimes we are going to try to select input UK in the following manner: G of xk, some function of the state at time k. Okay, so we will select the input sometimes as a function of the state. This means that into this system I'm actually applying a form of state feedback. Okay, so this is called the state feedback for the system, because we are taking the state and then we are passing it through a function and we are applying the input as a function of that state vector. So this is the state feedback. Then what is unknown here? Here G is unknown. That is called the feedback strategy or feedback policy for the system. Okay, so I want to apply a state feedback on the system, but I don't know which function that I need to pass the state to obtain the input at time k. So here, instead of therefore finding the inputs directly here, I will instead try to find the function g. Okay, in that case we are going to try to optimize the system with respect to a feedback rule. So that is going to give us the optimal state feedback controller for the system. But here you see that this feedback rule is a function of the state. Most of the times we are going to see that we can't know the state exactly. Okay, sometimes this y of k, the output function, this y of k is just equal to xk. There is no measurement noise, nothing here. So in that case, I know exactly what the what the state is, because the output that I measure would be exactly the state. But sometimes, and it is most of the cases, state will not be known directly, because in many cases we would have a measurement noise in the system like this. Therefore, the state will not be known exactly. That means that I cannot use such a feedback rule because I don't know what the state is. But instead of this, I can actually find the feedback rule which is in the following form. So the feedback rule would be in the form of G of yk. So sometimes knowing only the last output would not be beneficial. So sometimes we are going to make this function a function of all the previous outputs. Okay, so this is going to be called also a feedback rule for this system. And in this case, the feedback, the input, is a function of the previous outputs of the system. So then the state is going to be hidden from us. Okay, and we're going to see that such mathematical models, mathematical dynamical system models, will be called hidden Markov models. In that case, the state would be hidden behind these outputs, and by seeing the outputs, we need to try to control the state in an optimal way. Okay? So this is a stochastic optimal control, and sometimes when this system has some properties, so this is called a hidden Markov model in that case, and choosing the inputs sometimes is called Markov decision making. Okay, so choosing the state is a form of decision making, and controlling such systems would be Markov decision making, and such processes would be called Markov decision processes. Okay. So here you see that in this description, I will use some uncertainties here. So these uncertainties are everywhere in nature, and it is not only in measurement devices, it's also in the systems that we are trying to control. So we would always have uncontrollable inputs that we wouldn't know. So I've told you that we're going to know this. We're going to know that we are not going to know this WK, or we are not going to know this VK here. And instead, we are going to know the distribution of WK and the distribution of the measurement noise VK here. Okay? And based on their distributions, we are going to be able to take optimal decisions with respect to some criteria. Okay? So here, of course, these uncertainty representations would become really, really important. Then, when I have an uncertain system, knowing the state doesn't mean anything. I will never know the state, but instead, I will know its distribution only. Okay? So I will only know its distribution, and based on those distributions, I need to make some decisions. But before making decisions, I need to know how to manipulate such distributions, or how to use such distributions. And that is the topic of probability theory and stochastic processes. Okay? So in this department, in the undergrad level, we have courses for probability and stochastic processes. The course 230, for example, will be a prerequisite of EE557. Okay? So I will assume that you know probability theory, so how to manipulate these distributions. So in the first couple of lectures, I will try to give a review of the probability, but this review will be only a reminder. I will not cover any rigorous probabilistic theory here, and I will assume that you know probability theory. So if you didn't take any courses on probability theory, it will be very difficult to manage in this course. as I said, I will give a review of the probability theory in this lecture, but it is only going to be a quick reminder. So there is a full course on probability theory. Similarly, I will be using linear algebra a lot in this course, and it's going to be very important that you have taken a course like EE501, okay? Advanced linear algebra. So I will be talking about, for example, eigendecomposition of matrices, Jordan canonical forms of matrices, etc. So if you have taken a course related to linear system theory like 502, it is really going to be useful, but it's not really necessary for EE557. I will try to cover the linear system theoretic parts of these systems as much as possible in 557. So it is not a must to know linear system theory in this course, but it is of course going to be useful because we are going to be using some concepts from linear system theory. I will try to explain them as much as possible, but of course, knowing them beforehand would be useful. So this was a basic introduction for what EE557 is. And now I want to start with my review of probability theory. So I will erase all of this. So actually, it is not important what I have written so far. We're going to go slowly on these parts, and I'm going to repeat what I have already done. Okay, so let us start with review of probability theory. So here, I'm going to give you a reminder, and I will not be able to explain everything. So I will assume that you know these topics. So I'm doing this just to remind you what we're going to use here. And I would like to introduce some notation. So we're going to cover the course based on the main textbook that is given in the syllabus. And I will try to cover the concept as similar to the book as possible. Okay? So, but in order to be able to understand the book, then you're going to have to know its notation. And you will see that if you look at the pages of the book, all pages are filled with probability distributions. So in order for you to be able to understand the book, you would have to be introduced with the notation that the book uses. So here I'm going to start a description. So I have omega, F, and P. So this is called a probability space. And this is a triple quantity, and this is the beginning of the probability and random processes, probability theory and random processes course in our department. And here, the capital omega is the set of outcomes of an experiment. Okay? This is sometimes also called the universal set. Okay? So elements of these omega, this universe set, are the outcomes of an experiment. And F is the so-called sigma field. Okay? So this is field. Sometimes this is called sigma field or a Borel field of subsets of omega. Okay? And the subsets of omega are called events. So events is the subset of an event. Let me write. An event is a subset of omega. So this F, which is a field of subsets of omega, is filled with events. Okay. So this is a set which is filled with subsets of this universal set, and each subset is called an event. And we know that a probability function or a probability measure, which we show as P here, it is a function from the event set, from the sigma field to the interval 0, 1. Okay? So P is a function, and it takes an event in it, and then it returns a real number between 0 and 1. So this is called a probability measure. And then I'm going to, so if you remember the probability course, there are some axioms of this function. For this function to be a valid probability measure, there need to be some axioms satisfied by this function. But I'm not going to enter into such discussions here. So I'm going to directly enter into random variable. So Z, we call it a random variable. And this random variable is going to be a function from the universal set into real numbers. Okay? So now I'm only going to be considering a random variable, a real valued random variable, and then we're going to go into vectors, and then we're going to go into multiple vectors at the same time. So sometimes we show this random variable as a function like this. The book sometimes uses this type of notation to denote that this Z, it takes an omega, which is an element of capital omega in the universal set, and it returns a real number. So a random variable is nothing but a function from the set of outcomes into the real numbers. Okay? So we are going to use 3 probabilistic descriptions. So these are going to be equivalent descriptions for us. Okay? But you should know that in many cases, in especially rigorous mathematics, people would think that these are not equivalent. Because in engineering studies, we always assume that, except for some areas like information theory, etc., we always assume that density functions exist. Okay? But in mathematics especially, or in information theory under electrical engineering, people would always assume that densities might not exist. Okay? And in that case, they have to use more powerful or more general descriptions of probabilities. And as a result, lots of complicated theory would appear in rigorous mathematics and, for example, in information theory. So the first description, probabilistic description of the random variable Z that we're going to use is the probability distribution of Z. Okay? So in this case, I'm going to show this probability distribution with a capital P, and I will have a subscript here, which denotes the random variable here. And here I'm going to give this probability distribution a subset of real numbers, which is Z. Okay? And this is going to be P of the random variable Z inside capital Z. Okay? So this is a definition of the probability distribution of the random variable Z. It takes a subset of the real numbers, and it gives us the probability of the event small z is inside capital Z. Okay? So here, where capital Z is a subset of real numbers. Okay? So this is a function from the subsets of real numbers into the interval 0 and 1. Okay? So sometimes people would use, or the book uses, the following notation. This is the probability of omegas such that Z of omega is inside capital Z. This is the same thing. Okay? So the random variable is a function of omega, and which is inside capital omega, and this probability is nothing but the probability of the event which is composed of omegas which would satisfy such a condition. Okay? These are denoting the same thing. So this is the probability distribution of Z, and in many cases this would exist. Okay? And as I go to the other descriptors of the random variable, they might not exist sometimes. But in this course, we're always going to be assuming that the density functions, which is going to be the third description that we will see here, are existing. Okay? So therefore, all of the descriptions here will be equivalent for us. But since the book uses different descriptors at different places, I'm actually introducing them to you one by one. So the second descriptor that we're going to use is the cumulative distribution function. Function of Z. This is sometimes called just a CDF. Okay? Cumulative distribution function. And I'm going to denote it as f subscript z, and I will put here a variable. In this course, I'm not going to differentiate between the random variables and their realizations, except in some singular cases where that would be useful. So sometimes, not sometimes, if you are in a mathematics department, you need to show the random variable like this, f of z tilde, and the realization of the random variable with z. Okay? So it is really a nice notation, and mathematically it is the most meaningful, but here I'm not going to be using such a notation because it is really cumbersome to apply all the time. Okay? I'm already spending too much time in these lectures. So last semester I have actually recorded the second half of 501, and unfortunately my lectures were much longer than the allowed lecture hours. So I hope you can tolerate me in that. In order to be able to clear all the time, I'm trying to explain as much as possible. And since I cannot get any feedback from I'm in a meeting room in our department. It is 11 o'clock in the evening now. So definitely I cannot get any feedback here when I try to teach in front of the board. So I'm assuming that nothing is clear when I write something onto the board here. In a real classroom, I would look in the eyes of the students and try to see if they have understood what I have written here. But somehow it happens that I assume in these lectures that nothing is clear, so I'm over-explaining things here. So I hope you can tolerate this. So here I will show the subscript z and the realization as the variable psi here, and this is going to be defined as probability of z is smaller than or equal to the number psi. Okay? So this is the cumulative distribution function of the random variable z, and it gives you everything that you would need when you want to use that random variable. And the third description of the random variable that we're going to use is the probability density function. This is the most common, and it's going to be the case in this course. That is the probability, the density function of Z. So this is abbreviated as PDF. And this is going to be, as you all know, the derivative of this function. So Pz of Z is going to be d over dz, the derivative of the cumulative distribution function with respect to its argument. Okay? So this is the PDF that we are going to use. So this is a definition of the PDF. Here I need to distinguish between small p and the capital P. Okay? So I will use small p subscript the random variable. Sometimes I will also skip the subscript as well. When it is clear from the context, I will skip the subscript as well. So capital P is going to show the distribution and it's going to take subsets. On the other hand, the small p is going to denote the probability density function, and it is going to take the values of realizations as its argument. Okay? We know that all PDFs are actually satisfying this type of property. Pz of Z is always larger than or equal to 0. And actually that tells us that this cumulative distribution function is always non-decreasing. And we know that the integral of Pz of Z dz is always equal to 1. Okay? These are the properties of the density functions. So here, as I told you, for us in this course, all of these three descriptions will be equivalent. Okay? But in the general theory, these are really not equivalent. There are some random variables which you can define for which density functions do not exist. In that case, these two, the higher two, can exist sometimes. And so the most general case is this probability distribution. So for a random variable, this always exists. Then the second chance is that this can exist, and the third chance is that this can exist. Okay? So the people in information theory or in mathematics working on stochastic variables or stochastic systems, they always work with the probability distributions because the densities might not exist. So when you try to work with only probability distributions, then the mathematics that you are using turns into something called measure theory. Okay? And if you are poisoned with measure theory, then you never accept the fact that densities exist. Okay? You always assume that densities do not exist, might not exist, and you always use this distribution to be able to develop your theory. So since these quantities might not exist, so we can always, if this does not exist, then we can always go to this, or we can always go to this. But as I told you, since we will always assume that the density functions exist, then I will be able to express the lower descriptions here in terms of the upper descriptors here. So for example, here I already expressed the density function in terms of the cumulative distribution. We can express PDF in terms of CDF using this expression. Okay? What about expressing the CDF in terms of the probability distribution? I can actually do that as follows. So f of z of psi. So I will just try to write this in terms of this function p of z, and instead of this event here, I need to actually substitute here a subset of the real numbers. Okay, so just compare these two expressions. So what should you choose, capital Z, for these two events to be equivalent? Okay, and that is nothing but this interval minus infinity and psi. Okay, so I can express the CDF in terms of the probability distribution just in this manner. Okay, why is that? Because if Z is inside this subset, then Z is smaller than or equal to psi. Okay, these two events are equivalent if I choose capital Z as this interval here. So also it should be possible for me to express this density function in terms of the probability distribution as well. Okay? How can I do that? So Pz of Z, that is equal to, I will just try to write this probability first. So that is going to be, let me put here psi. This is going to be Z between psi plus dz, and I will have psi here. And this is a probability, and in order to turn it into a density, then I would need to divide this by dz. Okay? And dz is an infinitesimal element here. So this is the description of the density function in terms of the probability distribution of the random variable. Okay? So sometimes the book shows this probability just like this. Pz dz over dz. Okay, this probability, the book shows it in this manner sometimes. Okay? And in that case I just get the description. Pz of dz is dz times this PDF. Okay? So now this completes the scalar random variables. Now I'm going into the random vectors. So let us say z is a random vector. And in that case, z is a function from the set of outcomes into Rn. Okay? And here I can actually define these three descriptors for the random vector as well. Okay? So the distribution function Pz of capital Z would be the same. Okay? I'm showing the probabilities probability operator as P braces here. So if you see capital P and braces, that means the probability operator of the overall space. And if instead you see capital P and the standard parentheses here, then it would be the probability distribution of the random variable. Okay, so this is again Z in capital Z. And in this case, just this Z changes, where capital Z is a subset of Rn in that case, because I'm considering a random vector in this case, and it takes its values in Rn. Okay, so the only thing changing here is this R changes into Rn. And here I will define the CDF, and CDF would be just this. I will again write the variable psi here. This is the probability of capital Z is smaller than psi. And here you need to understand this inequality as an element-wise inequality. Okay? So this Z is a vector of some elements, and psi is also a vector. And when I write Z is smaller than or equal to psi here, you need to understand that the first element of Z is smaller than psi 1. The first element of psi. Second element is smaller than the second element of psi, etc. So this is an element-wise inequality. So that I have some events here. The first element is smaller than the first element of psi. Second element of Z is smaller than the second element of psi. So these are all individual events, and I'm looking at the intersection of those events. And the third probability description of a random vector would be just the PDF of the random vector. Okay? And it is Pz of Z. The density function is nothing but d over dz times f zz. It's the same thing as this one. Okay? In this case, just z is a vector. So this is the derivative with respect to elements of Z. So if you have multiple elements, if Z has two elements, then this is del square over del Z1, del Z2, etc. All right? So now I can talk about expectations with the random vector. Of course, I could have talked about expectations in the scalar case, but since I can already define the vector, it is going to be much more descriptive. A scalar is a special case of a vector. So let us look at the expectation. So the expected value of a quantity, so I have Q of Z, a function of this random vector would be defined as follows. So it is the integral of over the whole space of Qz times the density function of Z dz. Okay? So sometimes the book shows this integral as follows. This integral should be familiar to you. I'm taking the expected value of Qz. That means that I need to multiply it with the density, and then I have to integrate. Okay? Sometimes the book shows the same integral as follows: Rn Qz times Pz of dz. This shows exactly the same thing here. Okay? So remember how I have written the density Pz of Z in terms of the distribution. This is nothing but Pz over dz over dz. Okay? So when I take this term here, then Pz of dz, the probability of the infinitesimal here is nothing but Pz of Z times dz. Okay? So what the book does is nothing but replacing this multiple here. It is actually, in that case, a probability, and with the probability distribution of the random vector here. Okay? So if you are working on information theory, for example, you would always write integrals like this. Okay? Why is that? Because the density function does not have to exist. So if you write an integral in this manner, then you are implicitly assuming that the density function exists here. Instead, you can write the same integral using this notation, and this integral notation covers the cases of random variables for which the density function might not exist. Okay? But for our purposes, for our engineering purposes, these two are going to be the same. Okay? Now we're going to select this function q of z as some specific variables. Okay? For example, when q of z is equal to z itself, when q is the identity function, this expectation would be, I will show it as z bar, would be the expected value of z. Okay? And this is nothing but the integral z, pz of z, dz. And the integral is over the whole space of the random variable. Okay? So that is the expected value of the random vector. And this is called the mean of z. And the second case of the function qz is this. Sorry. It's just going to be this function. So I have z minus z bar, and, sorry. This is going to be just this. Norm of z minus z bar square. I will subtract the mean from the random variable, and then I will take the norm square of the resulting vector. Okay? Then the expected value of that function would be the so-called variance. And this is the variance of z. And it is a form of uncertainty measure. If the variance is large, then the more uncertain the random vector is. And the third case, so this was the second case, third case is q of z is equal to z minus z bar and z minus z bar transpose. All right? And then the expected value of that quantity is going to be called the covariance. Sigma z is equal to expected value of this outer product. Remember, this is called an outer product, and it's a rank 1 matrix. A vector times its transpose is a rank 1 matrix in general, if the vector is not equal to 0, and we are taking its expected value. And this is called the covariance of z. Okay? So what is the relationship between the variance and the covariance? So in this case, this is an n by n matrix. On the other hand, this is a scalar. Okay? Now I'm just going to take the trace of this n by n matrix. If you do not know what the trace is, then I can explain it as the sum of the diagonal elements. Trace of sigma z would be the following. Trace of this expectation. Okay? So expectation is a linear operator and trace is a linear operator. I can interchange it. So of course, there are some regularity conditions that has to be satisfied for interchanging such linear transformations. And here in this course, we are always going to assume that we can do that. So we are always going to be assuming that those regularity conditions are satisfied so that we can always interchange such operators. So I have expected value of trace of this outer product. So now I'm going to use a fact from linear algebra. Trace of AB is equal to trace of BA. For any two matrices for which I can multiply AB and BA like this, trace of AB is equal to trace of BA. And here I'm going to take A as this vector and B as its transpose. So I will interchange these traces, these vectors. So that is going to be, so that is a fact from linear algebra, and that is going to give me the following equality. This is the expected value of trace of Z minus Z bar transpose Z minus Z bar. Okay? And here you see that this is nothing but the transpose of a vector transpose of a vertical vector times the vertical vector itself. So this is going to be the norm square of this vector. Okay? So that is equal to expected value trace of Z minus Z bar square. And I have trace of a scalar here, which should be scalar itself. So I remove trace, but this is nothing but the variance. So we see here that the covariance of a matrix and the variance of a random vector would be related by the following expression. The variance is equal to trace of the covariance matrix. Okay? So we have found this expression. Now I'm going to be looking for another expression for the covariance matrix. For that I'm going to use the following expansion. If I have such a form here, such an outer product, then I can distribute these vectors. So I would have Z transpose minus Z bar Z transpose minus Z bar transpose, and I have plus Z bar transpose. Okay? And then I will take the expected value of both sides. So the expected value of the left-hand side is going to give me the covariance, and expected value of the first term is Z transpose. And expected value of the second term will be as follows. So this is the mean of the random vector, and it is a deterministic quantity. All right? The mean of the random vector is a deterministic, so the expectation can be taken only over the second variable here. So that is going to be Z bar times expected value of Z transpose minus, here I have the same thing, expected value Z times Z bar transpose, and this quantity is deterministic by itself. So I really do not have to take the expected value of a deterministic quantity. It gets out directly of the expectation. Okay? So here you see the following. So this is Z bar transpose. This is Z bar. So I have Z bar transpose here. This is negative. And I'm adding the same thing here. So these two are canceling. But that gives me sigma Z. The covariance is expected value Z transpose minus the mean times mean transpose. Okay? If the vector, random vector Z was a scalar, then I would be, the variance is expected value of the square of the random variable minus square of the expectation of the random variable. Okay? So I would have this type of relationship. So now it is the time for a remark. Sigma z, the covariance, is always a positive semi-definite matrix. Is always a positive semi-definite What does that mean? Again, we have some linear algebra knowledge here, so we need to interpret what positive semi-definite would mean. So I would just make a reminder here. If a matrix A is positive definite, if and only if X transpose AX is always positive for all non-zero X's. Okay? So this is a quadratic form. If it is always positive, so the positive definiteness is the generalization of positive real numbers, okay, for matrices. And matrix A is positive semi-definite if and only if X transpose AX is larger than or equal to 0 for all X. Okay? And remember that positive definiteness and positive semi-definiteness have some implications on the eigenvalues of the matrix. Eigenvalues of a positive definite matrix are always positive. Eigenvalues of a positive semi-definite matrix, they are always non-negative. Okay? So how can we show that a covariance matrix is always a positive semi-definite matrix? So I multiply the covariance matrix with A. Instead of X, I will use A here. Sigma Z and A. All right? This is the quadratic form for the covariance matrix. So this is A transpose, expected value of Z minus Z bar and Z minus Z bar transpose times A. So I can take this A transpose and A multiplications inside the expectation. That is equal to, because these are deterministic quantities. So I have A transpose Z minus Z bar times Z minus Z bar transpose A. So now you see a number here, Z minus Z bar transpose times A. A is a vertical vector, and Z minus Z bar transpose is a horizontal vector. So this is nothing but a scalar. This thing is a scalar. And here I have its transpose. A scalar transpose is itself. Okay? So these two numbers are actually equal to each other. So this is equal to expected value of Z minus Z bar transpose A square of it. Okay? So I'm taking the expected value of a square of a number. All right? But that should be always greater than or equal to 0. So that means that this covariance here, this is true for all A in Rn. Okay? So the covariance matrix should always be a positive semi-definite matrix. So now I'm going to give a break, and in the next lecture we're going to try to cover the joint distributions or marginal distributions and conditional distributions, etc. But that's going to be all for this lecture. Thank you for watching. Bye-bye.